Hi, welcome to my channel. Today we have an interesting proof to go through. It involves an inequality with a whole bunch of radicals. So what we want to do is prove that the root of n to the power of root n plus 1 is greater than the root of n plus 1 to the power of root n. And we want to show that this is true for n values greater than or equal to 10. Now, what we're going to do is take the right-hand side and turn it into a binomial series through a sequence of clever moves. And once we've done that, we'll be able to gain some more insight along the way. So here's how we'll do this. So first, we'll take both sides and rewrite these bases with powers of a half. So here we've rewritten the radicals in the bases. Now what we'll do is we'll square both sides. And when we do this, this exponent and this exponent multiply together, which gives us half the root of n plus 1, and then multiplied by this exponent, and that half cancels out. When we do the same trick on the right-hand side, the same thing occurs. So this half and this 2 cancel out, give us 1. So we're left with the following. At this stage, again, we'll take both sides, and now we'll raise them to the power of the root of n. When we do this, we now obtain this on the left-hand side, because these two exponents multiply together. And when these exponents multiply together, we're left with just n. So you see at this stage, we've cleaned up the right-hand side and eliminated all radicals. So things are looking a little more manageable now. One more trick will be to divide both sides by n to the power of n. Now, when we do this, the left-hand side, the numerator and denominator, both have a base of n. So we can simply subtract exponents. And that leaves us with this. And on the right-hand side, instead of having the same bases in the top and bottom, we actually have the same exponent. So what we can do is write the numerator divided by the denominator all to the same power of n. And at this stage, we're almost where we want to be. We'll take what we see here in the bracket and simply take n divided by n is 1, and 1 divided by n is 1 divided by n. And so we arrive here on the right-hand side. This is the binomial series. So what we're now going to want to do is work with the right-hand side to show an alternative way of writing it. So how can we do this? Let's go to a new board. So here we are now. We left off at this stage. We took our original inequality that we wanted to prove, and we're at this equivalent statement now that we hope to prove. And to help us out, again, we're going to take this right-hand side and expand it out using the binomial expansion. So on the right-hand side, what do we obtain? Well, the very first term of this expansion will have the coefficient of n choose 0. The remainder of this term will contain this first quantity to the power of n, and this second quantity to the power of 0. And every subsequent term, this bottom number will increase by 1, this will decrease by 1 in the exponent, and this will increase by 1. So this increases all the way to n, this will decrease all the way down to 0, and this will increase all the way up to n. So the next term will have this coefficient, then it will contain 1 to the power n minus 1, and 1 over n to the power of 1. Now let's throw in a couple of more terms here just to sort of see a general pattern. The next term will have coefficient n choose 2, and it will also contain 1 to the power of n minus 2 and 1 over n squared. We can continue this on all the way to the last term. With coefficient n choose n, and now this 1 will have reached a power of 0. And in purple, the 1 over n will have reached a power of n. So here, expanding this out, we obtain this series. If we clean things up here, what we now have is the following. N choose 0 is always 1. 1 to the power n is 1. And 1 over n to the power of 0 is 1. In the second term, n choose 1 is always n. 1 to the power n minus 1 is still 1. And 1 over n to the power 1 is 1 over n. Now, as we move on, n choose 2, n choose 3, n choose 4, all those other coefficients in the series, how we'll compute them is by the very definition of choosing. N choose 2 will be computed like this. This upper number, factorial, divided by this bottom number, factorial, times the top minus the bottom, factorial. And then we're left with multiplying by this 1 over n squared. As we go out to the last term, n choose n is 1. 1 to the power 0 is 1. And we have 1 over n to the power of n. So now let's see where this has taken us. 1 times 1 is 1. N times 1 over n. Well, these cancel to give us 1. And then what we have is this quantity here. We're going to do a little bit of shuffling around. We will take this quantity and shuffle it with this. So what we obtain is n factorial in the numerator. This n squared will take the place of 2 factorial. This will stay here, and this will take the place of n squared over here. Now the idea is to see in the next step a comparison of this series with another series containing factorials. And so writing it in this setup or this format will help us compare the two series more easily. And finally, we have 1 times this fraction, which is 1 over n to the power of n. So notice what we have here. 1 plus this quantity, plus all the rest of them. And all the other quantities, all the other terms within this summation will have a similar look to this, where we have n factorial on top, powers of n in the bottom, this difference of n minus 2, 3, 4 factorial, and then on the outside, this 1 over 2 factorial, and 1 over 3 factorial, 1 over 4 factorial, and so on until we get to this last term. What we see here, let's compare that to this series. Notice that this quantity right here is less than 1. How do we know that? If we come over here to the side, n factorial is n times n minus 1 times n minus 2 times n minus 3, etc. And down here we have n minus 2 factorial, which is n minus 2 times n minus 3, etc. So beyond n minus 1, all terms cancel. N minus 2, n minus 3, n minus 4, those terms cancel. N minus 2 factorial. So what we obtain here is this canceling with this, and n minus 3 canceling with n minus 3 all the way down. So we're really left with just this quantity here. You can see that that's n squared minus n divided by n squared. And we can view that as 1 minus 1 over n. So no matter our choice of n, especially since it's 10 or greater, if you remember at the beginning of the proof, we're proving our question here for n greater than or equal to 10. If n is 10 or greater, then 1 minus this quantity here, this fraction, is always going to give us a result less than 1. So this here is less than 1. And that's true for every other term that's in this series. So if we compare this to this, they're the same. This to this, they're the same. Now this to this, notice this 1 over 2 factorial here and this 1 over 2 factorial here. Those are equivalent. But up here, this 1 over 2 factorial is multiplied by a quantity less than 1. So this entire quantity, including the 2 factorial, will be less than 1 over 2 factorial here. And the same argument you can show holds for all the other terms in this series when you compare them one by one to what we have down here. So in fact, this entire series is less than this series over here. And if we take a look and expand this out a little more, just to see a few more terms, we're going to make another claim. We're going to claim the following inequality holds. 2 to the power k is less than k plus 1 factorial as long as k is greater than 2. Now, why are we making this claim? Well, let's take this series that we just obtained and compare it to yet another series. In this series, we have reciprocals of powers of 2. Now, these terms match, these are equal, 1 over 2 factorial and 1 over 2 to the power 1 are the same. Now starting here, 1 over 3 factorial gives us 1 over 6. 1 over 2 squared gives us 1 over 4. So a sixth versus a quarter, this fraction is less than this fraction. And the next term would give us 1 over 4 factorial versus 1 over 2 to the power 3. Now 1 over 4 factorial, that gives us 1/24th, but 1 over 2 cubed is 1/8. So this is smaller than what's down here. And when we continue comparing, we get all the way to this term compared to the last term, which in fact is this. And so still this is smaller than this by our claim. And therefore this entire series is less than this one. And what we can do even is tack on an extra power of 2. And that still keeps this bottom series bigger than the one above, because we're just adding on a little more to this series, which is already bigger than the one above it. And the reason why we're going to do that is because now we can isolate this partial series. And what we know is that this gives us a classic result. This is the sum of the reciprocals of the powers of 2. If we add up from I goes from 1 to infinity of half to the power I, this gives us 1. Now, of course, we'd have to sum all the way to infinity here for the series to actually be equal to 1. But we're only going to stop at n, although we don't have to. We can think of n as being 11, 12, 13, 14, or even all the way out to infinity. But only when we go out to infinity will this total 1. Otherwise, we'll have something less than that. So worst case scenario, this partial series can be no more than 1. And therefore, at this stage, we have 1 plus at most 1. So 1 plus at most 1 is 3. And therefore, this here is less than or equal to 3. What a beautiful spot to have arrived. From something so perhaps obscure or unmanageable, and we're maybe not quite so sure how this is going to get us anywhere, but we can see that really this summation, well, this power, really is no more than 3. So let's go to a new board and let's finish this up. So from the last board, our result that we obtained was that this power here, 1 plus 1 over n all to the power n, can be no greater than 3. And so originally our proof that we were tackling was that this quantity had to be greater than this quantity. If this can be no more than 3, then now we're left to prove that this left-hand side must be greater than 3. And so that original question with all the radicals, the root of n to the power of root n plus 1 being greater than the root of n plus 1 to the power of root n, that has now been rewritten in an equivalent form like this. So how can we show that this left-hand side is indeed bigger than 3 for n values greater than or equal to 10? Well, we're actually going to massage this exponent a little bit to give us something a little more manageable to work with. So this exponent here The first thing we'll do is factor out a root of n. And now we'll multiply this by unity by choosing to multiply by the conjugate of what we see in here over itself. Because we're multiplying by the conjugate here to here, all we have to worry about is multiplying the first terms and the second terms together. So what we end up with is this root of n hanging out there on the outside. This times itself is n plus 1 minus this times itself, which is n, leaving us with this in the bottom. And n minus n is 0, leaving us with 1 in the numerator. So if we multiply or distribute 1 to root n, we end up with root of n. And we now get this. One last trick we'll utilize is to divide every quantity here by the root of n. Dividing this by the root of n gives us 1. Dividing this by the root of n gives us 1. And then dividing this by the root of n gives us that. Now what we can see is we have 1 in the numerator. This radical over this radical gives us one big radical of n plus 1 over n plus 1. And from here, n divided by n is 1. And 1 divided by n is just that. So what we have now is this exponent rewritten like this. Now how is that useful? Well, what we'll do is we'll take both sides of this inequality and raise them to the power of 1 plus the root of 1 plus 1 over n. When we do this, we multiply exponents here, and that leaves us with just n. And on the right-hand side, we have 3 to the power of what we see in blue. Now it's left to show that indeed this is larger than what's on the right-hand side for n greater than or equal to 10. So let's take a look a little more closely at what we see on the right-hand side. The lowest n could be is 10. The highest it could be, well, is infinity. We can choose n to go out to infinity. When n is 10, this right-hand side becomes 3 to the power of 1 plus the root of 1 plus a tenth. 1 plus 0.1, so 1.1. When n tends out to infinity, 1 over infinity will give us 0 and only 1 left in the radical. So the root of 1 is 1, plus 1 is 2. Now it turns out, well, we know this is 9, so that's the lowest that this can be. It's the lowest value that the right-hand side can take is 9. And this is the largest value that it can take. 1 plus the root of 1.1 is 2.049. So 3 to the power of 2.049 is probably 9 point something. In fact, it's 9.5. So what does this tell us? Well, with n being 10, the lowest value possible, it does turn out to be true that it is larger than 9.5. When n is 11, will it be greater than what we have on the right-hand side? Well, of course, because now, as n gets larger, as n tends to infinity, this quantity on the right-hand side approaches 9. So on the right side here, we'll have 11 is being greater than something less than 9.5. And when we compare 12 to the right-hand side, it'll be greater than something that's even smaller than what we had previously. So these values will decrease, decrease, decrease to 9, while these values on the left increase. And so certainly from 10 onward, as n grows, the right-hand side here will fall below 9.5. And so it is true then that this is greater than this, which completes our proof. So thanks for watching.